So previously we discussed the reaction of an unsymmetrical alkene like 3-methyl one butene with a couple of different electrophiles. We have seen the reaction of HBr, in which we get an addition of bromine to the more substituted carbon and an addition of hydrogen to the less substituted carbon. We also saw that this molecule can rearrange, and so we'll get a reasonable amount of product in which I have 2-bromo, 2-methylbutane, about 60% of this, about 40% would be 2-bromo, 3-methylbutane. We've also seen how we can react 3-methyl-1-butene with an acid catalyst and then add the elements of water across the double bond. We found that when Br- and H2O are competing as nucleophiles, that water, although it's neutral and bromine is negatively charged, that water is the stronger nucleophile of the two. And just before we dismissed class the other day, we quickly went into some mechanistic detail regarding the addition of Br2 across the double bond, and we found that we would Br2 add the 2 bromine atoms in an anti-fashion without any rearrangement. So what we want to focus on this particular podcast is the mechanism regarding this reaction. So let's consider our substrate and our nucleophile. Normally, we don't think of bromine as being electrophilic. We don't think of it as being electron deficient because it's a nonpolar compound. However, if we look at a quantum model, and in particular an electrostatic map, we find that when we have this halogen approach and nucleophile, a region of electron density, and certainly we can think of the carbon-carbon double bond of 3-methyl-1-butene as being nucleophilic. Notice that the electron density shifts. This is called an induced dipole, such that the bromine that is closer to the source of electrons in the pi bond is electron deficient and is electrophilic, while the bromine that is farther away has an excess of electron density and is not as electrophilic. In the electrostatic map, please remember that areas of blue indicate a deficiency of electron density. Areas of red indicate an excess of electron density. This is an induced dipole, and it is very temporarily lived. They will easily shift when this density from the carbon-carbon double bond goes away, but it persists long enough to facilitate a nucleophilic attack. And so when we just complete drawing the Lewis structures here, the lone pair on the bromine atom becomes pretty significant in this mechanism. So I'm just going to complete the details. And before, when we looked at how the bonds are made and the nature of the intermediate, if you really want to break down what's going on in organic chemistry, look at the nature of the intermediate. So at the bottom of this slide, I want to compare and contrast what we learned on the previous podcast with HBr, where the hydrogen is our nucleophilic atom. And let's go back to what we know, what we've learned previously. First, and what we know is that the pi bond, the pi electrons make a bond with the hydrogen, which gives up the bond, the 2 electrons that it was sharing with bromine to bromine. I actually produce an intermediate, a carbocation, that is capable of rearranging and the rearranged carbocation is what accounts for the major product, because it will be attacked by Br minus. We see some pretty interesting differences here. First of all, electrophilic bromine and the non-electrophilic bromine. And of course, the nucleophilic pi bond. Strongest nucleophile attacks the most reactive electrophile. This bond is going to be made from this carbon. What one of the lone pairs can now do is it will, in a nearly simultaneous manner, donate 2 electrons to make a bond with what normally would become the carbocation, while at the same time allowing the 2 electrons that were shared with the second bromine to go to that bromine and generate bromide. If we're interested in looking at a transition state, pi bond begins to break. Carbon-bromine bond begins to make. Another carbon-bromine bond begins to make. While the bromine-bromine bond begins to break. In terms of charges, partial negative charge is formed. Partial positive charge is actually formed but spread out or delocalized in this three-membered ring. And once the dust settles and we're looking at our intermediate, we actually have a choice of ways we can draw this intermediate. Either this bond is made above the plane of the pi electron density, so don't think of this as coming out as much as it being on top of the pi density. And of course our other choice is we can approach this below the plane of what was the pi bond. These are not bonds being broken. These are actually intended to show the bromine atom approaching the pi density from below the plane. Now, if a picture is worth 1,000 words, then a good animation based on quantum mechanics is worth a whole book. So what I would like to do now is introduce you to a very interesting resource, very valuable resource. I will be posting this link on pause. It's ChemTube 3D. And so in ChemTube 3D, we have a symmetrical alkene, ethene, and we have molecular bromine. The bromine that is closest to the pi density of the carbon-carbon double bond is electrophilic and has a partial positive charge. Bromine that's further away is not electrophilic. Best nucleophile is going to be the loosely held electrons. And remember, they're loosely held because the orbital overlap of p orbitals is not end on end like a sigma bond, but rather side on side. And so if we look at how this reaction proceeds, I'm going to pause this as we reach the transition state, and then I'll pause it as we reach the intermediate. Transition state. Notice that the carbon-carbon pi bond is beginning to break. Carbon 1 bromine atom beginning to make. Carbon 2 bromine atom bond is beginning to make. Bromine-bromine bond is beginning to break. As we go through, we'll let this go forwards and backwards once. We find now that we have Br minus, and I have this three-membered ring, and we call this three-membered ring a bromonium ion intermediate. Bromonium ion intermediate. Now the whole trick with this is this positive charge is delocalized onto all three atoms that comprise this bromonium ion intermediate. But the positive charge is going to be stabilized by different extents depending upon the stability of the atom. And we already know that if it were on this carbon, even though this is not a carbocation, it's primary-like. If it's on this carbon, it is secondary-like. And if it's on this bromine, actually, if you think about it, we should quickly reject that hypothesis because bromine is typically meant to be a monovalent atom. It does not easily engage in two bonds. So if you compare the three atoms, the most stable positive charge will be on the carbon that I'm circling in green. This will be, in the next step, in the final step of this reaction, the most reactive electrophile. The most reactive nucleophile is this Br minus ion that we produced. Best nucleophile attacks the best electrophile. So before I actually draw this, let's actually look at this on the animator. Now this animator is based upon quantum mechanical calculations. So it takes into account things like atomic size, charge density, charge distribution, polarizabilities. And if we look closely at this model, it's really difficult to envision a path that bromide could take to attack the carbon on the same side to where that bromine is attached. So we really have to have attack from the back side of either of these carbon atoms. Now there's no difference between these carbon atoms in this particular example, but there is a difference in the one that I have drawn. And the attack must be from the back side. And if you attack it from the back side, this bond will have to be broken. So you would push arrows, tail of the arrow, tip of the arrow, tail of the arrow, tip of the arrow. Now you have a bromine atom that is to the left and a bromine atom on the bottom carbon that is to the right. This is anti-addition. Let's take a little bit closer look at what this looks like. I'm just going to choose one that I drew. So I'm going to show the bromine having already attached from the top of the pi bond plane. And I'm going to show Br minus attacking from the backside. When I attack from the backside, the old carbon-bromine bond must be broken. This must be going in, this continues to come out. So if we draw our final product, we get the anti-vicinal dibromoalkane. Just one other way that we could represent this that may make a little bit more sense to y'all. If we look at a Haworth projection where it is ring-like, then we would see one bromine going above the plane and one bromine going below the plane. This is another way of thinking about anti-addition. Now, just as we discussed in class with our previous set of reactions, let's make one minor change to this system. And the only change I'm going to make, same substrate, same reactant, I'm just going to throw another reactant into the mix. As soon as it lets me change the canvas color. There we go. Same substrate. Br2, just like we had before, but now we're going to have water in our reaction system as well. So the nature of the intermediate is going to be exactly the same. In fact, I'm going to go ahead and draw this intermediate now. And just to be different, now I'm going to show the other enantiomer. Again, we'll talk about this more next week when we do stereochemistry. Best electrophile is still this carbon. So now I have a competition between Br minus and H2O. And just as we discussed previously, in order to really determine which one is the strongest nucleophile, we're making an overriding assumption that equates nucleophilicity with alkalinity. We cannot always do that, but in this reaction scheme we can. We need to examine the conjugate acids. The conjugate acid of Br minus is, of course, HBr. The conjugate acid of water is H3O+. The pKa of HBr is -8, while the pKa of hydronium is 1.74. This means that HBr is the stronger acid. Which means its conjugate base is weaker. Therefore, H2O is the stronger base. And we're going to go ahead and equate that with being the stronger nucleophile. So just as we saw before, one of the electrons attached to the oxygen atom of water attacks. From the backside, you get net inversion. And we get a molecule called a bromohydrin. The OH will be going into the plane, or excuse me, coming out of the plane of the screen, while the bromine goes into the plane of the screen. It's still anti-addition. So both of these reactions are amazingly similar. Mechanistically, they're identical until we get to the last step. So to recap, what we've learned thus far about mechanism: This brings our total reaction mastery to 4. HBr with this substrate. We get rearrangement and a tertiary alkyl bromide. If I add HBr in the presence of water, again I'll have rearrangement, but I'll have a tertiary alcohol. If I react this with Br2, there is no rearrangement. And I will get an anti-addition of 2 atoms of Br across a double bond. And if I add Br2 and water, I get a bromohydrin, and it will be the OH that attaches to the more substituted carbon. So this serves as a really nice introduction on how we can handle adding Br2 and Br2 with water across a double bond. No rearrangement occurs because we do not have an integer carbocation intermediate. We have a partially positively charged carbon ion intermediate. In fact, we shouldn't even call it a carbocation, but we can have a directing group electrophile effect if we have an unsymmetrical alkene. So the big difference between the first 2 reactions that we podcasted earlier in the week and the 2 we're discussing now is the 2 previous reactions, you had to look out for rearrangements. These 2 reactions in this podcast, no rearrangements have ever been observed in nature. So in the next podcast, I'm going to look at how we can add hydrogen across a double bond, and also we will delve into nucleophilic addition across a carbon-oxygen double bond.